Welcome to TalkTensors, the show where we dive deep into the latest machine learning research.
Great to be here.
Today we're looking at a really interesting paper, BriLLM Brain-Inspired Large Language Model.
Yeah, this one caught my eye too. It's proposing something pretty different from the Transformers and GPTs that, dominate everything right now.
Exactly. They're calling it BriLLM, and it's built on this idea of signal, fully connected flowing, SIFU, they shorten to SIFU.
Right, SIFU. And it operates on a directed graph structure. It's fundamentally a brain-inspired approach, trying to get around some of the issues we see with current LLMs.
So what are the big claims here? Why is this a potential shift?
Well, they're highlighting a few key things. First, full interpretability. They claim you can understand what every single node in the model is doing.
Okay, that's a big deal compared to current black boxes.
Huge. And then there's the theoretical support for, get this, infinitely long in-gram models without the model size exploding.
Infinitely long. How does that even work? We'll have to dig into that.
We will. Plus, they suggest it might have innate multimodal support baked in, so handling text, images, maybe other things more naturally.
Interesting. And they have an early version, right? BriLLM Chinese?
That's right, V0.5. It's working with about 4,000 Chinese characters, 32-dimensional node width, and predicts sequences of up to 16 tokens long right now.
Only 16 tokens, okay.
Yeah.
But the performance?
Here's the kicker. They say its performance is already comparable to GPT-1.
Wow. Okay, so a small model, relatively speaking, hitting that kind of benchmark suggests there's real potential here, maybe a different scaling curve entirely.
Precisely. It suggests that maybe with more resources, this architecture could go somewhere really interesting.
All right, let's take a step back then. Before we get lost in the weeds of BriLLM itself, why the need for something new? What are the problems with Transformers and GPTs that this is trying to solve?
Yeah, good question. The paper points to two main drivers, scalability and, as we touched on, interpretability.
Yeah, scalability, we know LLMs are huge and getting bigger.
Exactly. And Transformers especially have this computational cost issue with long sequences. That attention mechanism where every token attends to every other token, it scales quadratically with the sequence length. So double the length, quadruple the computation, roughly speaking. It's a massive bottleneck for efficiency.
Right. It makes processing very long documents or conversations incredibly expensive.
Incredibly. And then there's the interpretability problem.
The black box issue.
Yeah. We can train these incredibly powerful models, but understanding why they make certain connections or predictions at the parameter level, it's extremely difficult.
So we can't easily debug them or fully trust their reasoning.
Pretty much. BriLLM aims for transparency. The goal is that each part, each node has a potentially understandable role. The authors also make the point that transformers work very differently fundamentally from how we think the human brain processes language and information.
And the brain is kind of our only existing proof of general intelligence, so maybe aligning closer makes sense.
That's the argument, yeah. Explore architectures that might be, let's say, more biologically plausible, or at least inspired by those principles.
Okay, that covers the why. Let's get into the what. What is BriLLM structurally, and how does this SIFU mechanism actually function?
So BriLLM is structured as a bidirectional graph. You can picture it like a network. Each node represents a token, a word, basically, in its vocabulary.
Okay, nodes or words. What about the connections?
The edges, the connections between these word nodes, aren't just simple links. They're actually fully connected neural networks themselves.
Whoa, okay, so each connection has its own mini network.
Essentially, yes. And guiding the whole process, deciding which connections get activated, is what they call the energy tensor. Think of it like a dynamic signal that flows through this graph.
An energy tensor. How does this signal, this energy, decide the next word?
It's driven by the SIFU mechanism, which has three main parts. First, the graph topology itself, fully connected, directed, and bidirectional connections between nodes.
Meaning signals can flow both ways between any two words.
Potentially, yes. Second, there's a dynamic weighting system. The strength of the signal transmission between nodes isn't fixed. It changes based on the learned relationships, the functional correlations between words.
So words that often follow each other will have stronger signal paths.
Kind of, yeah. The weights determine how strongly one influences the next. And third, there's a nonlinear activation module. This is a mathematical function, like GLU in their case, that helps the model learn complex patterns and hierarchical relationships as the signal propagates.
Okay, so if I input a sequence, say the cat sat on the day,
Yeah.
the signal starts at the, flows through, activating connections based on weights and activations.
Exactly. The signal flows from the input node, and the subsequent nodes get activated based on where the maximal energy flow occurs.
So the next word, predicted, is basically the node that receives the strongest signal, like the path of least resistance for this energy.
That's a great way to put it. The path of maximum energy flow, or least resistance. And to train it, they use negative sampling.
Negative sampling, how does that work here?
So if the correct next word after love in a context is meat, the model is shown that correct path, love meat, but it's also shown incorrect paths like love apple or love iron.
Ah, I see. So it learns to push energy towards the correct path and away from the wrong ones.
Precisely. Maximize energy for the right answer, minimize it for the distractors.
Got it. That clarifies the concept. Now, the how do they actually formulate this mathematically? The nodes, the edges, the signal flow.
Okay, so each token, each node, is represented as a hidden layer of neurons with a learned embedding vector. Just like in other models, this vector is a numerical representation capturing the word's meaning or function.
Standard embedding, okay.
Yeah.
And the edges, the neural nets between nodes.
Those are modeled by fully connected matrices and bias vectors. These essentially define the transformation the signal undergoes when it passes from one token node to another in both directions.
Right. So walk me through the forward process. I give it an input sequence. What happens step by step to predict the next token?
It starts with an initial signal shape, which they currently set as just a uniform vector, simple starting point.
Okay.
This initial signal then gets expanded into what they call the signal tensor. This is done by taking a weighted sum of the signals from the preceding tokens in the sequence. The model learns these weights during training.
So it's looking at the history.
Exactly. Then this signal tensor flows from the current token node to all other possible next token nodes. This flow calculation involves passing the signal through those edge matrices we talked about and applying the nonlinear activation function, GLU.
And that calculates the energy for each possible next word.
Yes. The final step is choosing the next token. They identify the outgoing edge, the connection to the next potential word that has the largest energy. They define this energy as the L2 norm, basically the magnitude of the resulting signal tensor for that connection.
The path with the biggest signal wins. Makes sense.
Yeah.
And training this must be unusual.
It is quite different. For every single training sample, they essentially build an individual neural network on the fly.
An entire network per sample. That sounds intensive.
It does. This network connects the input nodes through all the potential paths that could follow. Then, right at the end, a softmax layer looks at the energy tensors of all these possible paths and calculates probabilities.
Okay.
They use a target vector that points to the correct next token and then standard cross-entropy loss to adjust the weights throughout the network, the embeddings, and the edge matrices to make the correct path more likely next time.
Fascinating. A very different approach to training. Okay, let's talk about their experiment. BriLLM Chinese V0.5. What did they use and what did they find?
They used a chunk of Chinese Wikipedia, about 100 million characters. They chopped sentences down to 16 tokens maximum and used a vocabulary of the 4,000 most common Chinese characters.
Right. And the implementation details.
Built using PyTorch, they use sinusoidal positional encoding, which helps the model know where tokens are in the sequence, GLU activation, like we mentioned, and the AtomW optimizer, which is pretty standard.
And the model size.
Embedding size was 32. This resulted in a total model size of around 16 billion parameters.
16 billion. That's actually quite large, especially compared to the 0.1 billion for GPT-1 you mentioned earlier.
It is large, yes. That's an important point we'll come back to.
Yeah.
They trained this on 8 NVIDIA 800 GPUs for about 1,500 steps.
Okay. And how does the computational cost stack up theoretically compared to transformers?
They state the complexity as ONV.D2, where N is sequence length, V is vocabulary size, D is embedding dimension.
So linear and sequence length N, which is good.
Yes, that's the key advantage over transformers' quadratic scaling with N.
But it's quadratic in V, the vocabulary size, and D, the embedding dimension.
Correct. So bigger vocabularies or richer embeddings increase the cost quadratically, which is a trade-off.
Right. So what did they actually see in terms of performance with this V.5 model?
They showed some examples, a case study. It could complete partial sentences or phrases, sometimes quite coherently, even on test samples it hadn't seen during training, like completing a known book title.
So it learned some meaningful patterns.
It definitely did. But as you'd expect this early on, there were also examples where the predictions were less accurate or didn't make much sense. It's clearly still early days for turning and scaling.
Of course. Which leads us nicely into limitations and future directions. What are the main hurdles they identify?
Well, the biggest one right now is just raw computational power and data. They acknowledge the current model is limited by the training resources they had. They strongly suspect performance would improve significantly with more scale.
Makes sense. What about the model size itself, that quadratic dependence on vocabulary?
That's definitely a challenge. A vocabulary of 4,000 is tiny compared to modern LLMs. Scaling that up quadratically would be problematic. However, they do propose potential solutions.
Like what?
Things like using sparse representations, maybe not having dense connections between all tokens, or sharing parameters, especially for less common words. They estimate this could potentially save up to 90% of the parameters.
Okay, so there are ideas for tackling that scaling issue. What about training efficiency? You mentioned building a network per sample.
Yeah, that makes parallel training inherently difficult compared to batching and transformers. It's a bottleneck. They suggest exploring approximate ranking strategies.
Meaning?
Maybe instead of calculating the energy flow to all 4,000 possible next tokens, you could focus the computation on a smaller, more likely subset for each training step. That could potentially speed things up and allow for better parallelization.
Interesting. Let's circle back to that multimodal potential. How exactly might BriLLM handle images or sound inherently?
The idea stems from the interpretability. Because each node is, in theory, understandable and not hard-coded to only represent language, you could potentially have nodes represent visual features or audio patterns or concepts derived from other data types.
So you could connect these different modality nodes within the same graph structure.
That's the vision. And because the core mechanism is the signal flow, integrating new modalities might not require completely retraining the model from scratch, which is often the case now. It could be a more seamless integration.
And that claim about infinite n-grams without size increase seems almost too good to be true.
Well, it's theoretical. The architecture allows for it because every node can connect to every other node. There's no inherent limit, like a fixed context window size imposed by the structure itself. But in practice, for the model to actually learn those super long-range dependencies, you'd need to train it on data with such dependencies, likely for a very long time. The capability is there structurally, but learning to use it effectively is another matter.
Got it. Theory versus practice.
Yeah.
What about that initial signal shape? They mentioned using a uniform vector, but speculated it could be more.
Yeah, they found even a random start worked, which was surprising. It led them to think this initial signal could act like a prompt.
Like prompt engineering in GPT.
Potentially, yes. A way to guide the model's generation or behavior without needing explicit fine-tuning, just by setting the starting state of the signal flow. It's an unexplored area, but could be quite powerful.
And supervised fine-tuning, SFT itself.
Yeah.
Adapting BriLLM for specific tasks like question answering.
That's flagged as key future work. They haven't explored SFT yet. And relating back to the performance comparison.
The 16 billion BriLLM versus 0.1 billion GPT-1.
Exactly. While comparable performance is impressive in one sense, the vastly larger size of BriLLM needed to achieve that suggests it might have a much higher emergent ability threshold.
Meaning it needs to get much, much bigger before we see the kind of complex reasoning or task performance we get from current large models.
That seems plausible based on these initial results, yeah. It might scale differently, maybe needing more parameters initially to get basic competence, but perhaps scaling better in other ways later on.
So summing up the comparison, BriLLM differs from transformers in how size relates to input length. It aims for full interpretability and might handle multimodality differently.
That's a good summary. They lay out these differences clearly, highlighting the distinct design philosophy and the resulting trade-off.
All right, this brings us to our novel notions segment. Given this unique brain-inspired approach, especially the SIFU signal flow, what speculative research ideas does this spark?
One thing that really jumps out is this least resistance principle for signal flow. Could we leverage that for memory?
How so?
Imagine adapting the dynamic weighting system not just for next token prediction, but to actually encode long-term memories within the graph structure. Information retrieval wouldn't be about searching an index. It would be about initiating a signal related to your query and seeing where the energy naturally flows.
So the memory is queried by the signal flow itself.
Exactly. Think about training BriLLM on a huge knowledge graph. A query signal might naturally gravitate towards the most relevant interconnected concepts, maybe bypassing the need for explicit attention over vast databases. Memory access becomes an emergent property of the signal dynamics.
That's a really cool, very different take on memory and AI. What else?
Well, combine that potential multimodality and the interpretability. Could you build truly integrated sensor-motor agents?
Meaning agents that perceive and act in a more unified way.
Right. Instead of having separate modules for vision, language, action planning, what if they were all represented as interconnected nodes in a single BriLLM-like graph? Sensory input nodes, vision, sound, touch would influence the signal flow.
And the least resistance path wouldn't just predict a word, but maybe an action.
Precisely. The signal flow through this integrated graph could directly inform motor commands. It moves beyond just fusing modalities at the start or end. It allows for this continuous dynamic interplay between perception and action, potentially more like how biological systems work. You could train such an agent in simulation, learning complex tasks through this holistic signal processing.
Wow, integrating sensing, reasoning, and acting through this unified signal flow. That's ambitious, but really compelling.
Definitely ambitious. And of course, we should add the disclaimer. These are speculative ideas, jumping off points for discussion and maybe future research. Lots of hurdles to overcome, for sure.
Naturally. Purely speculative fun for now. Okay, so to wrap up our deep dive today, BriLLM presents a really fascinating alternative to the transformer paradigm.
It really does. Brain-inspired, focused on this dynamic signal propagation.
Offering potential paths towards better interpretability and maybe more natural multimodal integration.
Though, as we discussed, it's early days, there are significant challenges with scaling, training efficiency, and proving out those complex emergent abilities.
Absolutely, but it's definitely research that pushes the boundaries and opens up exciting new questions about how we build intelligent systems.
Agreed. And if you want to get into the nitty-gritty, definitely check out the paper. We've linked it in the show notes.
It's worth a read. And that leaves us with a final thought. Could the real future of AI depend less on just scaling up what we already have, and more on fundamentally rethinking computation, perhaps drawing inspiration directly from the brain itself? Thanks for tuning in to TalkTensors.